1, 2. Yes, I never know where to put this mic so that it is as audible as possible. Okay, hello, Bashana. Now we are going into our grade 12 live for physical science. We are ready, willing, and able. Please, if you have joined in, tell us where you are watching from. Tell us how you feel about tomorrow. How are the exams going so far?
That's a grade 11, please. So I guess the grade 11's trying to be.
Oh no, so this is for grade 12. But I'm sure you can pick up a thing or two. If you're in grade 11, yeah, actually, grade 11s, I'd advise you to join as well. I'd strongly advise that you join. Yeah, please, I'm looking forward. Moses Machetlani. He's from Limpopo, our favorite province.
Yes.
M Dark, 12 a.m. Dark. Nama pseudonyms like. It's from Gauteng. Ngubeko Makubane. Awu, wakwaZulu. Abakagumbana, abakabani. Ngubani. Yeah, but abakabani. She's Tagazel. How?
I don't know. Oh, Ngubani. No, I don't know.
Google there quickly. Sizombiza ngesithakazelo.
Let's Google quickly.
Yay! Opelung, sending love from the Northern Cape, Kimberly. Hey, hello. All right, guys, please just be mindful. We are still working on the network. I know that it might not be as clear as we like, but hopefully as we continue with the stream, the clarity will get better. Unfortunately, where we are, it was raining, and for some reason, I don't know whether the network lines have been disturbed or whether it's because of traffic. I'm not really sure. But hopefully, please listen in. We'll send you the document that we are working from so that you can be able to follow. So we'll start exactly at 6 o'clock. Né? We'll start at 6 o'clock.
I'm still looking for Interza.
Oh, sneak up. Oh, I'm with our fave, Shez.
Hi.
Behind the scenes, making the things, doing the things that make the pot. Umbovu. Huh? So much. Oh, Sugan in my door. We've got Khonzi Rasekhala from Limpopo. Nangu Vesia, KZN, Peter Maritzburg, Nepierville. So what paper are we doing? Please just note, we'll send the paper. It's a mixture of questions and which were compiled. It was compiled in Limpopo, and it's really a mixture of questions, and really some of those questions are oh my goodness, really interesting questions. Michelle, I'm aware that it is blurry. Unfortunately, we've had bandwidth issues, network issues. Please just bear with us. I'm hoping that it will become clearer as we go along. But if it doesn't improve, at least you'll go through the question. You'll be able to understand as I go through them. And I'll try and write as big as possible. Ne?
Yes.
Yeah, just to compensate for that. Right, we've got 1 minute to go. Grab your glass of water, glass of coffee, and we are going to start in just a moment. Sorry, can I? What do they call this thing? Coaster.
A coaster.
Andikho bed.
Bandwidth, please.
Eish, Nkosi yam. Yeah, man, and not it's getting worse. The Limpopo Big Show. Yes, that's the one. That's the one. I'm using that paper, the Limpopo Big Show. I see someone, Michelle.
Oh, let me link it.
Yeah. Please just send it to them so that they can download it. Oh, guys, the question's there. Yeah.
Please let them know about our student resources. We have a link on Linktree where they can access a lot of question papers.
All right. Good afternoon, everybody. Good evening, wherever it is that you are watching from. Thank you for joining us. Most of you will be writing Physical Science Paper 1 tomorrow. That is the national exam. We thought we would go through a couple of questions, and you let me know in this case, how to go about it. But there are a couple of questions that I've prepared that I thought were really, really interesting. So please tell your friends at school, tell your cousins, tell everybody, okay, that we are joining live. I'm hoping that as we go along that the stream will improve. Unfortunately, we've had quite a bit of challenges. Please note that we've got our resources on our link tree, and we will also just give you the link. There it is. The link is there. You can have all past papers. What else is there? Bursaries. Are they there?
No, bursaries are only
for
members.
Only for members, okay.
Yes.
What else?
It's all around student resources,
Okay.
study material.
Yeah, study material, student resources.
Yes.
By the way, in future, I'm going to be
Timetable.
giving you, publishing some books that we will make available for both mathematics and science. So there's a lot going on, guys, and there's a lot that we are still going to ensure that we give you so that you have more and more value. All right, now we're going to start in just now. So firstly, maybe I'll give you this advice later, but we've got sections that are kind of low-hanging fruit, right? And I wanted to start with this one because momentum is seen as one of those, but in the way in which this question is asked, there is a bit of a trick here or there, right? I know, Humulemo, sorry, that it's pixelating, but we'll try that as the stream goes on, that it will improve. All right, now let me get into the question, and then later on I'm going to give you some advice on what it is that you need to look out for and how to really approach tomorrow's exam for those of you that are writing. If you are in grade 11, it would also help you to listen to this live so that you kind of get a sense of what next year looks like. All right, so let's get into it without any further ado. Okay, right, so I've got this question from the resource. You can download that resource. The link is there. Oops, I'm not sure what just happened. Okay. Shaz, I'm not sure what I just did. Okay, let's see. Okay. Oh yeah, it looks like it just bombed out, eh? Okay, right, there we go. All right, thank you that it's recovered. Right, so let's start with the very first question. It says we've got a stationary steel ball, X of mass M, that collides with a moving steel ball Y, right, with that is 3 times its mass. So we know that the mass, if we say that the mass of X is M, then the mass of Y will be 3M. Right. They say after the collision, the two balls move together in the forward direction at a speed which is 75% of the speed of the steel ball Y before collision. So, if the speed of Y was V, what would be the speed of the two balls afterwards? It would be 75%. So, which means VF would be 0.75. Remember that 75 divided by 100 multiplied by V. But remember, the mass is still 3M and the other one is M. Right, now quickly, let's look at it. They say explain what is meant by isolated system as applied in physics. So we remember that when we talk about an isolated system, it is a system that has no external forces, right? So there are no external forces in an isolated system. So secondly, they say state the principle of conservation of linear momentum in words, right? Remember, in an isolated system, the total linear momentum remains the same. Or you can say in an isolated system, momentum before collision is equal to momentum after collision. Now, let's go to the very questions that we wanted. So they say show by means of appropriate calculations that this collision is in agreement with the principle in questions 4.2. Right, now let's find out what the momentum is before collision and let's compare it to the momentum after collision. So I'm going to take the sum of the momentum before collision. Okay. Right, so I'm going to say sum of momentum before collision, initial. All right, and I'm going to take the momentum after collision. Right, let's take the initial momentum first. So this is going to be, now remember, in this case, that's the momentum for ball Y plus the momentum, Py and Px. So the momentum for Y will be 3m, that's the mass, multiplied by the velocity, which is v, right? But in this case, the momentum of x before collision would be 0, so which means momentum before will be 3mv. Now, let's compare this with the momentum after collision, right? So the sum of the momentum final, right? So remember, it will be momentum of y plus the momentum of x. Right, so in this case, by the way, I should have chosen a positive direction. So I'm going to take the initial direction to the right as positive. So we know after collision, both of the masses were moving together. So that's going to be the mass of x plus the mass of y. And this is multiplied by their final velocity. So mass of y is 3m, mass of x is m, okay? And this is multiplied by 0.75, right? And so you've got 0.75 multiplied by 4, and that gives us 0.75v. Okay, I'll need to just switch this guy off. Right, so this is 4m multiplied by 0.75v, and so this gives us 3mv. So this agrees with the principle of momentum. Therefore, we've noted that momentum before collision is equal to momentum after collision. Right, and then finally, let's answer the last question here. They say, is the collision between the two steel balls, X and Y, elastic or inelastic? Use suitable calculations to explain the answer. Now, what do we know about elasticity? In this case, let's find out what is the kinetic energy of ball A, of ball X, and ball Y before collision. So the sum of their kinetic energies. So this will be EK for X plus EK for Y initial, right? So the sum of their kinetic energies before collision. Right, so this will be a half of M. Remember for X rather, it was moving at 0 before collision, or rather it was stationary. And for Y, that would be 3M multiplied by that velocity, which is V squared. So what do we get? We get 3 over 2 mv squared. Right, I do apologize. I had a live before this, so I can hear my voice is not really at its best. Okay, right, so that's the kinetic energy of the system before collision, right? Now let's compare it with the kinetic energy of the system after collision. Right, so sum of the kinetic energy final. Now remember, after collision, the two balls in this case were moving together as one unit. So that's going to be 3m plus m multiplied by 0.75 v squared. Remember that their velocity was 0.75. So we've got 3 over 2. No, sorry. That's a half. 3m times m gives us 4m times 0.75 squared, that's 4m, multiplied by 0.75 squared times v squared. So let's take that. So a half multiplied by 4 gives us 2, right? So 2 times 0.75 squared we get 9 over 8 mv squared. Now you see that there are two kinetic energies before collision and after collisions are not the same. So in this case, our collision is inelastic. Why? Because the sum of kinetic energy initial is not equal to the sum of kinetic energy final. Okay, so please just remember that. And the only reason I'm entertaining this question is because, please don't be alarmed tomorrow when, they give you questions that might not have, values in them, but that have a lot of variables. Okay, so please just remember how to go about that. Hey, yeah, this thing is really pixelating. As I did say, we do apologize for that. I hope that it will improve. Now let's go on to the next question. So you asked for work, energy, and power. I deliver, right? So let's go for it. So they say to us, we've got the force F acting at a constant, at 30 degrees, right, to the horizontal, causes a 6 kilogram block to accelerate. So this is not velocity, this is acceleration. So they are telling us this block is accelerating at 2 meters per second squared. Now what does an acceleration suggest? it suggests that there is a change in velocity. And if there's a change in velocity, it means that there is a change in kinetic energy, right? So now they say to us, when there's a frictional force of 3 newtons, okay? Right, now they say define the term conservative force. Remember that when we talk about conservative forces, these are forces whose work done does not depend on the path taken. So which means those forces essentially retain their magnitude as well as their direction. So by definition, we say these are forces whose work done does not depend on the path taken. Right, now they say classify frictional force as a conservative or non-conservative force. What is friction? Definitely it is a non-conservative force. And I want you guys to please remember, the moment we talk about non-conservative forces, there are 2 that I'm expecting. That's going to be frictional force as well as the applied force. Those are the 2 non-conservative forces that we always look at, especially in relation to force diagrams, right? Now, they say draw a labeled free body diagram for the block whilst it is in motion. Right. So there it is. So we know we've got the force F, okay? So I can draw that over there. Please remember to draw that big dot. That's going to be force F. But remember, in this case, if you're going to use acronyms, you must qualify what that force is, right? And then we know we are pushing to the right, so which means friction is opposing the motion. So I've got friction. Okay, so that's friction over there. Frictional force. So either you write down the name of the forces in full. So I would have to say here, this is the applied force. Right? And then I also have the normal force that is acting perpendicular to the surface. Normal force. And I've got gravitational force which acts vertically downwards. This is the force of gravity, or you can say that is the weight. Okay, so those are the 4 forces. If you didn't want to draw it that way, there's absolutely nothing wrong if you're going to draw the applied force here, right? So that's where our applied force is. That's our frictional force. Okay, that's the normal force. That diagram does look a little bit better. And we've got the gravitational force. Now, please, guys, try to make sure that your diagram is, kind of represents force of gravity, or let's just simply call it the weight. Okay, it's easier for us to do so. Right. So, remember to label your force using full words, or in this case, you can use descriptions on the side if you're going to prefer to use acronyms. Okay, right, so those are the 4 forces. Remember that the mark allocation that is given will show you, or will tell you exactly how many forces we expect. Right, now let's go to the next portion. They say state the work energy theorem in words, right? So remember, in words, we say that the work done on an object, or the net work done rather, on an object is equal to the change in kinetic energy, right? Now they say to us, use the work energy theorem to calculate the magnitude of force F. Right, now let's go through that together. So, in this case, I'm going to say the net work done, right? In this case, remember, changes kinetic energy. But I want you to keep something in mind, right, when it comes to this question. So when you look at the forces that are acting horizontally in this case, right? So what's going to happen is that the applied force, right, would have, is acting at an angle, and that's an angle of 30 degrees. And I want you to keep that in mind. So it's acting at an angle of 30 degrees to the horizontal, right? So let's go there. Firstly, there's no velocity that's given, but we were given the acceleration, right? Now, I want you to keep something in mind. So we know in this case that we were given the acceleration, right? 2 meters per second squared. And by the way, they didn't give us, okay, that's fine. They didn't give us the displacement, but I want you to keep this in mind. So Vf squared is equal to Vi squared plus 2 times A delta X, right? So I would know in this case that Vf squared minus Vi squared is equal to 2 times A. What was our acceleration? Our acceleration was 2 meters per second squared, right? So that's 2 times our acceleration multiplied by delta x. So I'm going to say this is 4 multiplied by delta x. So that's Vf squared minus Vi squared. Now I'm showing you this way so that you'd know what to do with that acceleration. There is another way in which we could have done this, right? We've got the mass, and in this case they told us that the mass is 6 kilograms. Right, so which means this is half times the mass, okay? Okay, I'm trying to remove this just so that we clear it. There is something a bit, okay. Right, another way that I could have done this. Now remember, ladies and gents, F net is equal to MA, right? But what do I note in this case? What is my net force? That means when I look at net force, that would be the mass, that's 6, multiplied by the acceleration, which is 2, right? So what am I looking for? I'm looking for the work done, in this case, by the net force, right? So this is going to give us F net multiplied by delta x. Now, I want you to keep in mind, guys, what is my net force in this case? We've got the applied force and we've got the frictional force, right? Those are the two forces that are acting in line with this, right? So maybe to make things a little bit easier so that I get rid of, so F net multiplied by delta x, the cos of the angle theta. So the angle theta in this case, because it's accelerating in the horizontal, we always say it's the angle between direction of motion and the force in question. So that will be 0 degrees, right? Because it's accelerating in the direction of the resultant force. Now, maybe I did not even need this. We'll come back to it if we do, right? Now, remember we said that Vf squared is minus Vi squared, rather, is equal to 2 times delta x, right? That's 2as, right? Or 2a delta x. So this will give us 2 multiplied by 2 delta x. And what you can do is that we can divide, in this case, by that delta x, right? Now, but what is the net force? Right, so it's the force F multiplied by, now please remember in this case, so our force F is acting at an angle of 30 degrees to the horizontal, right? So, which means force F is acting, there's a component of F, so we're going to say F the cosine of 30 degrees, right? So we're talking about just F net in this case, right? So that's F cos 30 minus, now please I want you to note in this case, so we divided by delta x on either side, so it's F cos 30 minus the frictional force, right? That's what F net comprises of, and in this case this will be equal to 4. So we are looking for force F, so that's F the cosine of 30 minus our frictional force was given to us as 3 newtons, right? 3, that's equal to 4. If I take this to the other side, F cos of 30 is equal to 7. And if I divide both sides by cos 30, I will get, what would be 7 divided by cos 30? Right, I get force F to be equal to 8.0, yeah, let's just say 8.08 newtons. So that's how we are going to use our work, energy, and power in this case. Now, you couldn't use work done by, oh well, I suppose you could, because there's no change in potential energy in this case. Of course, there are other ways in which you could have answered this question, but I just wanted you to note that it is possible for us on the left and on the right hand side to be able to get rid of that delta x. Okay, right, so that's how you are going to answer that question. Right. Sikulile kanye sikulile sibuyi. Right, I see you say you don't understand. Please, if you can maybe explain to me what it is that you do not understand. Okay, sorry if I butcher your name. I am trying. The comments are moving as very fast, so I try to catch up with them. Ne? Right, so I want us please to move on to the next section. Right, I'm trying to cover as much as I possibly can during this live. So I had a question that I thought was really interesting for us to look at. Right, now this is based on electrostatics. Okay? Huh?
Can you borrow me
The phone, okay. Right. Has the quality improved?
No, it hasn't.
Okay.
I want to try something.
Do you have your router on?
No.
Oh, okay. All right. I was just wondering, could it not be that it's connected to that now?
I'm thinking if we switch platforms.
Switch platforms. Okay. How?
I think it'll work.
How so?
If we go live on TikTok, they won't be able to see.
I don't know, yes. Sure, do you think we can? Actually, I think because we've already started.
Yeah.
Sorry guys, we're really trying to get...
They're not focusing at all, they just keep on commenting quality. So
okay, I see. Okay, all right, guys, please allow us to maybe try this. Huh?
it's not bad though, it's getting better.
Okay.
This is what.
Yeah, it's getting better. Okay.
Let's
All right.
stay here.
Okay, all right. All right, so I think we made a decision that we're going to continue with this live. We do apologize about the quality thereof. That's something, unfortunately, we couldn't do anything about. We just seem to be having a network issue. But please stay on. It is getting better. The quality is getting better. So hopefully by the time that we reach the end, it would have improved significantly. Right, so let's go on to this question. So they say to us, we've got a diagram below that shows a positive point charge Q1, all right, a second point charge Q2 that may be positive or negative. So Q2 is the one that we don't know whether it is positive or negative, right? They say the distance, and a spot labeled P, all on the same straight line. They say the distance between the two charges is the same as the distance between Q1 and the spot. So both distances are the same, and you can see there they've used the designation R, okay, for that. So that is what it looks like, right? Now they say to us, with Q2 present, the magnitude of the net electric field, P, right, is twice what it is when Q1 is present alone. Okay, right. Now, firstly, so remember they are talking about the net electric field, right? So, in this case, they say describe an electric field. Remember that an electric field is the area where electrostatic force can be felt per unit charge, right? That is the definition thereof. Now, they say given that Q1 is 0.5, positive 0.5 microcoulombs, calculate Q2 when it is positive. All right, now please, guys, stay with me on this one. Firstly, we know that the net field is said to be 2 times the field due to Q1. Okay? Let me call it E1 instead. So that's 2 times. So I'll draw the electrostatic field pattern or diagram right now, the vector diagram just now, right? But I just want us to get that force. So that's going to be KQ1 divided by R squared. Now remember, we were not given the distance R, okay? So that's going to be 2K multiplied by 0.5, or rather let me say 2 times 9 times 10 exponent 9 multiplied by Q1, that's 0.5 microcoulombs, and this is divided by R squared. Okay, right, now that is the net electrostatic field. So I'm just going to have a so that's 2. In fact, even if we had not calculated, so that's 2 times 9 exponent 9 multiplied by 0.5. Shares, you are intimidating me. What's happening? Minus 6. Right. So I get a value there which is 9,000 over R squared. Now remember, what does that represent? It represents the net field. Now let's talk about what that looks like, right? So think about it. If Q2 is positive, so if you look at that positive test charge, that's over there, right? We were already told that Q1 is positive. So what is Q1 going to do to the positive test charge? It's going to repel it, right? So which means going to have E1 being to the right, okay? But then when Q2 is also positive, what is Q2 doing to the point charge? Remember, at any point, we assume that we've got a positive test charge. Then the field, in that case, E2, right, would be equal to, E2 would be to the right as well. So the net field would be as a result of E1 plus E2, okay? Right, so I want you to please note that E net would be equal to E1 plus E2. Now, one thing that I want you to note, guys, is that we already have, right, the field, right, the net field. So that means in this case, if it was due to E1 and E2, in fact, let me write it down so that you can be able to see it. So this is going to be 9,000 divided by, okay, R squared, right? Now E1, remember, we said it was half that. So that's going to be a half of that, which is a half of 9,000. Remember, E net was twice that. So this would be 4,500. That's a half of 9,000 over R squared, plus what would be our field E2, right? That would be K Q2 divided by R squared as well. In fact, let me just do this. So that would be K. Now remember, what is the distance between Q2 and the point charge? You'll see that the distance is R plus R. So that distance will be 2 times R, but we still need to square it. Okay, right. So if I subtract these two, if I take this to the other side, now we've got 4,500, so that's 9,000 over R squared minus 4,500 over R squared will give us 4,500 over R squared, and this would be equal to 9 times 10 to the power 9 multiplied by Q2 divided by, please, I want you to note in this case, okay, I just want to switch this off again. So this is divided by 4R squared. Right, guys, I want us to note in this case, we can get rid of that R squared by multiplying, but what I do on the left, I will do on the right. So that R squared cancels out, and that R squared will cancel out the R squared. And all I need to do is just cross multiply there, right? This is over 1. So I've got 4 multiplied by 4,500, which will be 18,000. Yes. 9 times 10 to the power 9 multiplied by Q2. And so if I divide both sides by 9 times 10 to the power 9, okay, and that gives us a value of Q2, okay, that's 18,000. All right. So in scientific form, I get that to be 2 microcoulombs. Right. So which means if Q1 is positive, or rather if Q2 is positive, then I know that Q2 will be equal to a positive 2 microcoulombs. Okay, right. I hope that you were able to follow that. Now, in the next one, say that if Q2 is negative. Now, please, guys, I want you to stay with me as I go through this. Now, note this time around. Remember, we said at P we've got a positive test charge, right? So what's Q1 going to do? Q1 still continues to repel, right? It's pushing this guy in the other direction. But what is Q2 going to do now that it would be negative? It would attract the point charge towards itself, right? So which means E2 is in that direction. But remember, we haven't changed anything in terms of the E net, right? They still said that the net field is twice, right? Where is that? Yeah, the magnitude of the net electric field P at P is twice what it is when Q1 is present alone. So the net field is twice. So now, please, I want you to stay with me on this one, right? So if I'm looking at this, now please note, I've got E1 pushing away. I've got E2 attracting this guy. All right. But what do I know about E net? So E net will be equal to, I'm going to still take the direction to the right as positive. That's going to be E1, or rather, yeah, E1 minus E2. Now remember, they are opposing each other, so now we are going to subtract that. But what do I know about E net? It's 2 times E1, right, is equal to E1 minus E2. So if I take that to the other side, 2E1 minus E1 would give us E1, right, is equal to, so 2E1 minus E1, that would give us, yeah, that would be minus E2. All right, now, remember, in this case, I've got K Q1 divided by R squared. That would be minus K Q2 over R squared. In fact, I can even cancel out the K's, but please be careful. That distance between Q1 and Q2 is still not the same, right? So let's put in the magnitude of Q1. So we said Q1 is 0.5 microcoulombs. So that's 0.5 microcoulombs divided by the distance between the two, right, which is R squared, right? The distance between Q1 and the point is R, but Q2 and the point are 2R meters apart, right? So this would be 2R squared. So all we need to do again, so this is going to be minus, so this would be equal to that's minus negative Q 2 over 4R squared, which is 0.5 times 10 to the power negative 6 divided by R squared. And again, ladies and gents, we can get rid of that R squared. So that would be R squared this side multiplied by the R squared, and that would cancel that out. And so so Q2 would be equal to, well, in both instances, that's 2 times negative 2 times 10 to the power minus 6 coulombs. All right, so Q2 would be negative, I'm just wondering if I did the right thing on the first one. Please just check for me there if I did the right thing. Okay, when I was taking them, because we could have also done the same thing mathematically, right? Okay. My whiteboard namhlanje is doing funny things, eh? Right. Please just bear with me. Okay. I think at this rate I might have to restart it, yes? Okay. All right. Yeah, just check in with me. So I wanted to, the first one, remember when both of them were going in the same direction, right? We found out that E1 and E2 were going in the same direction. So we said E net is equal to E1 plus E2. And we know that the net field was 2 times that of E1. Yeah, we essentially going to get the same thing in both cases. Okay, right. So I just wanted to show you, in this case, as I said, this resource really has some amazing questions. Right, now I'm going to go to the next one on electrostatics. Okay? Oh, it has gotten better.
Yes.
Oh, thank you. Okay, right. Okay, right, I see someone is telling me about that 4r squared. Okay, thank you for that. Right, now let's go on to the next one. Now, the reason why I wanted us to look at this question is because it involves some vectors. And it is possible for us to get something on vectors tomorrow, where we are looking at the triangular law of vectors in equilibrium, or in this case where we need to use our components, right? So they say to us a small spherical insulator of mass 80 grams. So we know that the mass is 80 grams and the charge is 0.6 microcoulombs. So there it is, the charge is 0.6 microcoulombs, right? It's hung by a thin light wire, and a charge of minus 0.9 microcoulomb is held 15 centimeters away from the sphere and directly to the right. So the wire makes an angle theta with the vertical, right? Now they say to us, neglect the effects of air resistance, right? So firstly, they say define the term electric field at a point. We've already done so. Right, now they say draw the electric field pattern associated with Q1 and Q2. So we've got a positive charge as well as a negative charge. So please, I want you to note, ladies and gents, right? I'm going to draw those. Right, so they are attracting each other. So our field pattern is going to look like this. Okay, so please just make sure that your diagram, hey, and you guys draw diagrams that look like spiders. Okay, please make sure that all your lines do not cross each other. That's the first thing, that you indicate the direction with your arrows, right? And that from the positive side, so positive side, always the field lines are always moving away from the positive. So I'm going to indicate that there, they're moving away. They're moving away from the positive. They're moving towards the negative. So our field, or our field lines, are moving towards the negative. Now, there's also what we call field line density, right? Now the reason why I want to mention that is that the charge Q2 was bigger than the charge Q1. So when I look at your diagram, that needs to come out, right? I need to be able to see which of the two charges is bigger than which. So I'm going to draw a bit more lines, a bit more lines on Q2. Please, all you need to make sure is that those lines do not cross each other. So please keep that in mind. Now, let's go on to the next question. They say, draw a labeled free body diagram for a small spherical insulator, right? For the small spherical insulator. So, I want you to note, what are the forces that are acting on this guy? So, firstly, it is the tension of that string. But secondly, it's the gravitational force. Remember that holds it down. But thirdly, that's going to be the force of attraction by Q2, right? Or you can say the electrostatic force there. Now you've got three forces, and what do we know about Q1? Q1 is stationary. So which means, in this case, our vectors are at equilibrium. So please label the force diagram clearly, because they said labeled. Okay, so the tension on string, the electrostatic force, or let's say the force of attraction, sorry for that spelling, and we can say this is the weight or the force of gravity. Okay, perhaps, yeah, maybe it might help also to just indicate that angle theta over there. Right, now that's our free body diagram. They say state Coulomb's law in words. So remember that Coulomb states that the force between 2 point charges is directly proportional to the product or to the magnitude of their charges, and inversely proportional to the square of their distance apart, right? Because we're dealing with point charges, we don't need to mention the word center. All right, now let's go on to the next part. So they say to us, calculate the angle theta. So guys, there are two ways in which we can do this, right? Firstly, I can either use my vector diagram, right, where I consider components of a force, right? Alternatively, what I can do is I can use the triangular law of vectors in equilibrium. I like this law because it just makes things so much more easier. So think about it. In this case, the triangular law of vectors in equilibrium says if three vectors are at equilibrium, they can be represented by a triangle, right? And you'll see that all the vectors are head to tail, right? With each side taken in order of its magnitude and direction, right? So what happens? Okay, so that guy becomes 90 degrees, right? That's between the vertical. So this is our weight, okay? And this is the force of attraction, right? Now, note this would form our angle theta. And what can we do? We can find out both of those forces, the weight as well as the force of attraction, isn't it? Right, so let's start with Coulomb's law. F is equals to K, Q1, Q2, divided by R squared. That's 9 times 10 to the exponent 9. This is multiplied by the charge on Q1 0.6 and the other 0.9. Please, we don't need to put in the sign. Times 10 minus 6, 0.9 times 10 to the power minus 6. And this is divided by the distance between them. That distance was given as 15 centimeters. So remember, centi, you divide by 100, right? So that's going to be 15 divided by 100, which gives us 0.15 squared. Now let's work out what the magnitude of that force is quickly. It's minus 6 multiplied 0.9, exponent minus 6 again, and this is divided by 0.15 squared. All right, I get a force of 0.216 newtons, right? And then, now that's the force of attraction. And then I can work out what the weight is. Remember, I was given the mass of this guy. So that's mass multiplied by gravitational acceleration. The mass was 80 grams. Now, please remember, in physics, we always work with kilograms. So that's going to be 80 divided by 1,000 multiplied by 9.8. Okay. So that's 80 over 1,000. That's multiplied by 9.8. So that gives us 0.784 newtons. Now note, guys, that means that we can now find out what is that angle over there. Now, if we use our trig ratios, we have the opposite side and we've got the adjacent side. So which means the tan of angle theta will be opposite over adjacent, and so theta will be the arctan of, now remember the opposite side, that was our force of attraction, that's 0.216, and the adjacent side was our weight, which is 0.784. Okay, and shift the 10 of 0.216 divided by 0.781. All right, and that gives us an angle of 15 degrees, 15.46 degrees. Okay, right. Now, for those of you who may perhaps prefer the other method would have involved, I like this one to be quite frank with you. The other method involves using components of a vector, right? So remember, if I look at that cable or the tension of the string there, right? So in this case, it means the force of attraction is equal to the x component. So I'm going to call it Tx, right? So you're going to say Tx, which is equal to the tension. Now notice, it's in Tx is on the opposite side of that angle theta. So which means Tx would be T, the sine of angle theta, right? This would be equal to Fa. And we found out what Fa was. It was 0.216. 216. But you also have Ty. Now, what is Ty? It is the vertical component It's the vertical component of the string, right? But remember, that is acting against gravitational force. But what is Ty? That's T, the cosine of theta. That would be equal to 0. What was it? 0.78. 0.874 newtons, right? And notice now you've got two equations, T sine theta, T cos theta. You can divide those by each other. It gives you exactly what we had, the tan of theta, and ultimately you can get that. I find this quite tedious in my opinion, but if you prefer it, you can use that method. Okay, right, and that's the method that's why I wanted us to calculate this. Now they say to us, calculate the tension in the wire. So if you had used my method, what you would have done in this case is that now that you've got, so there's your tension over there, you can use any of the trig ratios, right? You've got the force of attraction, you've got the opposite, you've got the adjacent in this case. So you can say T, either use Pythagoras or you can say the sine of, so sine of theta is equal to opposite, that's the force of attraction, divided by the hypotenuse, which is T. So which means, guys, please just bear with me, my board is glitching a little bit. So I keep trying to erase stuff and it doesn't. Okay, so if I cross multiply, I'll have T sine theta is equal to that force of attraction. And all that you can do is divide both sides by sine theta. And so T would be 0.216. But now that we know the value of theta, this is divided by the sine of, Konye, what was our angle? 15.46. Okay, then you can get the value of theta. Alternatively, if you had used this method, I mean, it would be quite simple to go about it because you now have the angle theta, so T sine theta is equal to that 0.16 over there, and you can get the value of theta. I hope that this was helpful, guys. I want to jump quickly to electric circuits. Maybe let's jump into that. And I think we'll call it a day there. Ne? Yeah, hey, Nami, I'm exhausted. Hey. Yo. All right. So, there was another question, man. Okay, maybe let me do this. Is the way I opened that document? Yeah. Okay, let me do this. All right, so this is the paper we're using. Okay. Are you hearing knocks? Ha, ungavuleli ipogo. Okay. All right. There we go. So, in this circuit, right, in the circuit below, they say we've got a battery that has an EMF of 12 volts, right? So they've given this battery of 12 volts. They say the internal resistor of the emitter is very small, while the voltmeter has a very large internal resistance, okay? They say define the term EMF. Please, I hope that you know this definition, right? So we say that it is the total work done per unit charge, right? So V is the total work done per unit charge, right, within the battery, okay? Right, they say state the reading on V1 when switch S is open. Now please, I want you to note, when V1, or rather when switch S is open, there is no current that is flowing into the external circuit. And so what happens as a result is that V1 will read, right? There's no loss in voltage, so V1 will read the EMF. So V1 will have a reading of 12 volts. Okay, right. I did say that my board is glitching a little bit, and I think maybe that's the, okay. Right, so it will have a reading of 12 volts. Okay, guys, you will just have to just give me a moment. I just want to try and refresh this board of mine. Okay. Okay, looks like it's much better. Right. Okay, so it means that the reading will be 12 volts. Right. Thank you for your patience. So they say to us, the switch S is now closed. So we're going to close the switch. The readings of A1 and A2 are 2 amperes and 1.5. So A1, where is A1? So A1 is 2 amperes. And A2 is 1.5. Where's A2? This is 1.5 amperes. Right, so A1, I want you to note, is reading the total current. Now what's going to happen? When we reach that node, some of the current will go there, right? The red current. And some of the current will go there into R2 and R1 as the green current, but together they meet again to form the blue current, which is the total current. All right, so that is what our circuit would look like. So what does that tell us? That R2 and R1 are in series with one another. Why? They've got the same current passing through them. But it means that R2 and R1 combined are in parallel with R3. Okay, so they're in parallel with that 6 ohm resistor over there. Okay, right. Right, so we've got that 6 ohm resistor there. Right, so let's go on to the next one. They say state Ohm's law in words. So remember that the voltage voltage across a conductor is directly proportional to the current, provided that temperature stays constant. But I prefer it the other way around, that the current across a conductor is directly proportional to the potential difference, provided that temperature remains constant. Now let's be quick about this. They say calculate the reading on V1. Now remember, the moment we close the switch, right? In this case, what it simply means is that we are now, please note, it means we are no longer going to be reading the value of the EMF. Why? Because of that internal resistance, okay? So the internal resistance begins to kick in, right? So there we have it. So how am I going to get the external voltage? Right, now this is going to be quite simple, because I want you to note in this case, right, we have only the parallel combination in our circuit. So if I can get the voltage of my parallel combination, right, And what do I know about resistors in parallel? That the voltage is the same, right? Now, look at this. I've got the current that is passing through the 6 ohm resistor, and I've got the resistance of it. So I can be able to calculate V1 by simply saying V1 would be equal to, let's call it current I2. Right? So that's going to be current I2 multiplied by R. So that will be 1.5 multiplied by 6 ohms. And 1.5 times 6 will give us 9 volts. Okay, I hope that's clear. So in this case, the voltage across the 6 ohm resistor will be the same as the voltage across those two, right? Together, right? And in this case will be equal to the external voltage. Why? Because there's no other resistors outside of the parallel combination. Right, now let's go on to the next one. They say calculate the internal resistance of the battery, right? So we want to find what the internal resistance is. So we've got the total current, okay? We are given the EMF. Now we've got the external voltage, right? Now I want you to please note in this case that okay, maybe let me write it down this way. Okay, I've got a lot going on over there. Right, so I have E is equal to I into R plus small r. But what's the problem? The problem is that I don't know what the external resistance is. Why? Because I don't know what X is. So I can't use that calculation. So I'm going to say E, now please stay with me. This is equal to V external plus V internal, right? So my EMF is 12 volts. But you remember we just found the external voltage as 9 volts, which means V internal is simply going to be equal to 3 volts. But what is V internal? V internal would be the total current. Remember, which current passes through that internal resistance? It's the total current multiplied by the internal resistance. So that's 3. That's 2 amperes. And that's R. And we can divide by 2. And so R is 1.5 ohms. So that's how we are going to get that internal resistance. Okay, right, now they say to us, calculate the reading on V2. Now V2 is the voltage. Now please, I want you to note in this case, V2 is the voltage only across resistor R1. All right, please stay with me. So I know in this case that 1.5 amperes passes the other branch, right? So if 2 amperes in total is what I have, and 1.5 amperes passes through A2, how much current would therefore pass through the other branch? How much current would pass through this red side? Well, 0.5 amperes, because 0.5 plus the 1.5 would give me the 2, which is the total current. Now please, I want you to note in this case, so I might as well just erase all of this to make up a little bit of space. I was trying to teach my students a little bit earlier. All right. Now, so In this case, I've got, yeah. So I total is equal to I1. Please, for the sake of it, let me just call them I1 and I2. My total current is 2. My current there was 1.5 plus I2. So which means I2 will be equal to 0.5 amperes. Now, remember that in parallel, the voltage is the same. We know the voltage of those two, right? That's 9 volts. They have 9 volts between them. But is it possible for me to find out the voltage of the 4 ohm resistor? Absolutely. I know the current passing through it, and I know its resistance. So I'm going to say the voltage there across the 4 ohm resistor will be I multiplied by R. That's 0.5 multiplied by 4, and that would give me 2 volts. Right, now please remember, in series, what do resistors do? They will share the voltage, right? So that means, in this case, both of those have got 9 volts between them. So I'm going to say the voltage across the 4 ohm plus V2. So V 4 ohm plus V2 will give me V external, or I can say V parallel. Okay? So that's 2 volts plus V2, and this would give me 9 volts. And finally, ladies and gents, it means that V2 will be equal to 7 volts, not ohms, 7 volts. And that brings me to a very important thing, what I just did just now. Please just remember, it is important for you to keep the SI units correct, okay? Because you do lose marks for every time that you're going to use an incorrect SI unit, okay? Right, now let's go on to the next question. So now, they say the resistance of R1. So remember, what do we have now? We know the current that's passing here. That's 0.5 amperes. But we know now that this guy has 7 volts across there. So what do we do? All we need to do, in fact, if you don't mind, I'm just going to remove all of this so that I don't keep going up and down. So to get the resistor R1, I will say this is voltage divided by current. But which voltage? That's V2 divided by the current I2. So that's going to be 7 volts divided by the current, which is 0.5. And so that gives me 14 ohms. Right, so we got that resistor to be 14 ohms. Right, and finally, guys, they say to us, calculate the amount of heat produced in the resistor R3 in 1 minute. Remember, whenever we are talking about heat, we are talking about power, right? Rather, we are talking about energy, rather, that is dissipated. They said in resistor R3. Now, R3 is this guy. So what do we have there? We've got the resistance. So power is equal to, we know the voltage, we know the current, but I'm going to use the current formula. So that's I squared multiplied by R. So that's going to be 1.5 squared multiplied by the resistance, which is 6. Oh, sorry, I look at me calculating power. Work done, which is energy. That's I squared R multiplied by time. So that's 1.5 squared multiplied by the resistance, which is 6, multiplied by, they said, in 1 minute, right? So remember, we need to convert time in seconds. So that's 60 seconds. 1 minute is 60 seconds. So as a result, what will be our energy? Multiplied by 6, multiplied by 60. That's 810 joules. Okay, right. So that is how we are going to get the power that is dissipated by that resistor. Okay, now this is the last set of questions, and this had to do with a calculation. Whenever they ask you to calculate cost, right? Now they say to us, by the way, they love these questions, these theoretical questions. They say, will resistor R2, or rather they say the resistor R2 is now removed. So if I remove R2, in this case, what will happen? Right. I want you to note the first thing that I need to check every time that they remove a resistor, okay, is what will happen to the current, to the effective resistance, firstly, right? So I want you to note in this case, so I had 1/6 plus 1/, remember we got this to be 14 plus 1/18, okay? So that was the resistance then, right? If you took the resistance, that's 6 times 18 plus 6 plus 18, right? That's what you had. Ooh, I said that's supposed to be divided by. Okay, so that would be 6 times 18 divided by 6 plus 18. I'm trying to show you something. So if we were to find the effective resistance first there, our effective resistance would have been 4.5 ohms. But now once we remove that 4 ohm resistor, right, what are we going to have? We're going to have 6 ohms as well as the 14 ohm resistor. So now that's 6 times 14 divided by 6 plus 14. So I want you to note, our initial effective resistance was 4.5. Now it is 4.2. So what have we done to our external? We've decreased our external in that case, right? Now they say to us, will the reading on V1 increase, decrease, or remain the same, right? They love these questions. So just remember that whatever happens to the resistance will happen to our external. So our resistance decreased. So as a result, I will say my answer is decrease. And they probably will say explain, right? Now, all we are saying, right? Our external will decrease. Okay, so our external will decrease, and a decrease in our external, will increase the current. Okay, right? Note I'm taking it step by step, right? So a decrease in our external will increase the amount of current. So we know that EMF and internal resistance remain constant. So because EMF and internal resistance remain constant, it means that when we take our V external, so this is constant, but what will happen to a V internal? Because R remains constant, once I increase the current, then it means V internal will increase. As a result, V external will decrease. So just simply say in this case, the EMF and the internal resistance remain constant, and so therefore it means that V external will decrease. Okay, right. Guys, they like this question. I'd say to you, please make sure that you practice this, you have a look at it. But I've got also just a very good playlist as well on circuits. And then the last question. Right. Now they say to us an electric heater is marked 220 volts. Okay, 1,500 watts. Electricity costs 91 cents per kilowatt. Okay. Now they say to you calculate the cost of running this heater for 5 hours. Okay. Now remember, the cost is cost per kilowatt. So I need to have, per kilowatt hour rather, I need to have my power in kilowatt hours, in kilowatts. I need to have my time in hours. So already, fortunately, our time is in kilowatts. So cost will be equal to the energy multiplied by the rate. So the rate is the 91 cents, right? So my energy must be in kilowatts. So that's 1,500. Remember, I want it in kilowatts, so I'm going to divide by 1,000. So 1,500 divide by 1,000 to express it in kilowatts, multiplied by the hours, which is 5 hours. Okay, so now my energy will be in kilowatt multiplied by hours. And this is multiplied by, in this case, the rate, which is 91 cent. Okay, or you can say 0.91. Okay, so let's get that. So that's 1.5 times 5 multiplied by 0.91. All right, so the cost of running this heater will be 6 Rand and 83 cents. Okay, right, so the cost of running the heater for 5 hours will be 6 Rand and 83 cents. Right, and then finally, they say to us a hairdryer operates at a potential difference of 240 volts and a current of 9.5 amperes. It takes a learner 12 minutes to completely dry her hair. Hey, is that really how long it takes?
Even more.
Even more? Ay, no es tu case, man. Just kundana machisco. Eskom charges 147 cents per unit. Okay, calculate the cost of operating the hairdryer for 12 minutes per day for a month. Yay! That is born how much girls are costing us. Hey! Oh, the guys do dry their hair these days.
The guys have braids now.
Oh, hey guys, kundana machiscope, man. Just cut your hair. Okay. Right, so I need to get the power first. So power, that would be voltage multiplied by current. Okay, so this is 240 multiplied by 9.5. Hey, I wonder why was this only 2 marks. So 240 times 9.5. 2,280. No, that's not the cost of running the dryer.
Oh.
2,280 watts. Okay? That's the power. Now, we are using it for 12 minutes. Now, please remember, guys, that when I calculate the cost, I said it is the power in kilowatts. So I need to divide this by 1,000. So That will be 2.28 kilowatts, right? Multiplied by the time. Now, you need to convert 12 minutes into hours, right? So remember, in this case, 60 minutes make 1 hour. So 1 hour is 60 minutes. So how many hours will be 12 minutes? So you can just cross multiply there. So you can say 60H is equal to 12. So all you do is divide the minutes by 60. Right. So that will be 12 divided by 60. Right. That's time in hours. Right. Now we've got our energy in kilowatt hours, and this is multiplied by the cost, which is 1.47. Now remember, this is per day, isn't it? Right, so we need to multiply this by 30. Hey, let's see. So that's 2.28 times 12 over 60 times 1.47 times 30. 20 rand. So the cost is 20 rand and 11 cents, right? So that's what you would get. So just remember that you need to convert it into kilowatt hours, and in that case, convert it into kilowatt hours first, and then you can convert it into the cost. Guys, I will leave it here. Electrodynamics, we've done quite a lot of it. Please, guys, don't leave anything to chance. Continue to prepare. I think they might spring in a surprise or two tomorrow, but please don't be dismayed. Don't be intimidated by any diagram. Calm down. You know your strong sections. Start with those ones. What else? Do the most. Multiple choice. It depends. Né? For some of you, perhaps may prefer to do multiple choice last. I've always preferred to do it first because I find it mentally exhausting. Right? Once I do it last, my head is all over the place. But please, if you prefer to do it last, you can do so. But please do your best insofar as this is concerned. Now, I will be traveling on Sunday, so which means that I will only see you on Saturday, right? We said what time on Saturday? At 4.
For grade 12.
For grade 12s. Yeah. For grade 11? We haven't confirmed. Okay, right. So it's 4 p.m. Are you sure?
Do you want to do earlier?
No, I was thinking of later. Okay, maybe you can also advise. Okay, what time would work better on Saturday? We'll be doing paper 2. I do want to make sure that you guys are prepared. And please, whatever happens tomorrow, please just make sure that you do your absolute best. For those of you who've been doing well in physics, please don't be complacent tomorrow. Né? Make sure that you are sharp. Okay, you are as on your best side. And I really want to wish you all of God's best. It's really been a pleasure being with you. Thank you all 304 of you who are still there live. Nyabonu Zolega is crying a multiple choice. Multiple choice. Please watch my videos on multiple choice sections, and I promise you that you will be fine. You'll be fine. You'll be just fine. Wishing you all of God's best. I'll see you guys again next time. And please don't forget to subscribe, and please tell others. But for those of you who also would need maybe some additional help, I don't know at this stage if it's possible, but you can always get in touch with us. Our WhatsApp number 064 554 7199. Guys, I'll see you next time. Mwah, mwah. Shop, shop.
064 554
7199.
The topics we didn't cover, they are on our channel.
Yes. Topics we didn't cover are on the channel. You can splurge in terms of the videos.
Yes. We have guidance videos, the ones that you did with Nkosi.
Yeah, guidance videos are there. Shares is here giving you advice. Me right, man. Me right.
Alrighty.
Okay, I hope this session was good. We're closing it out.
Shop, shop.